Number of ways of selecting one or more objects from a group of n distinct objects is nc1 plus nc2 plus nc3 and so on ncn. Because we are selecting one or more means it can be one object means number of ways of selecting one object is nc1, or two objects means nc2, or three objects means nc3 or ncn. Because we are using r means what? nc1 plus nc2 plus nc3 and so on ncn. This is one way of explaining the answer. There's another possibility is each object is having two cases, that is either selection or without selection. That means 2 to the power of n possibilities. In that we have to subtract 1. Why? Because there is one cases where no object is selected. That's why it is 2 to the power of n minus 1. Next, number of ways of selecting r objects out of n identical objects is only 1. Because all the objects are identical, so whichever you choose r objects, it is only one way. That's why it is answer is 1. Third point, number of ways of selecting 0 or more objects from a group of n identical objects is n plus 1. It is based on the previous point. This r can be what? 0, r can be 1, r can be 2, and so on, r can be n. That means n plus 1 possibilities will be there. Fourth, total number of ways of selecting one or more out of p plus q plus r objects where p are alike of one kind, q are alike of second kind, and r are alike of third kind. That means here p objects are identical, means you can think as they are bananas, and if you are apples, and r objects are oranges, but they are identical. Now we need to choose what? One or more. That means p plus q plus r objects one or more means p plus 1 into q plus 1 into r plus 1 minus 1. Now this minus 1 corresponds to, there is only one possibility in this where no object of p, no object of q, no object of r is selected. That's why it is you have to subtract 1. Total number of ways of selecting one or more objects from p identical objects of one kind, q identical objects of second kind, and n different objects is p plus 1 into q plus 1 into 2 to the power of n minus 1. Now it is again based on the previous points. Because p objects are identical, so the possibilities are p plus 1, and q objects are identical, so the total possibilities are q plus 1, and n different objects are there. For each object we are having two possibilities. That's why 2 to the power of n, and we are subtracting 1. This one corresponds to, there is only one case where no object is selected. Next, fundamental theorem of arithmetic. Any natural number n greater than 1 can be expressed as a product of primes in a unique way. That is, n equal to p1 to the power of alpha 1, p2 to the power of alpha 2, and so on, pk to the power of alpha k, where p1, p2, p3, and so on, pk are all distinct prime numbers, and alpha 1, alpha 2, and so on, all are positive integers. Go through once again. N equal to p1 to the power of alpha 1, p2 to the power of alpha 2, and so on, pk to the power of alpha k, where p1, p2, p3, and so on, pk are distinct primes. Then how to find the number of divisors or factors of the number n, how to find the number of even divisors of n, and how to find the odd divisors of n. Because here p1, p2, p3, and so on all are prime numbers, I can choose p1 equal to 2, p2 equal to 3, and p3 equal to 5, and so on. They are distinct primes. So number of divisors or factors of n will become alpha 1 plus 1, alpha 2 plus 1, alpha 3 plus 1, and so on, alpha k plus 1. It is like p1 identical objects are there. That means I am denoting p1 as 2. That means I can choose 2 to the power of 0, or 2 to the power of 1, 2 to the power of 2, to the power of 3, and so on. So here we are choosing 2 to the power of 0 means 1 is a factor. That means 1, 2, 2 square, and so on, 2 to the power of alpha 1. So alpha 1 plus 1 possibilities are there. In the same manner, 3 to the power of 0, 3 to the power of 1, and so on up to 3 to the power of alpha 2. So alpha 2 plus 1. So that's why the product is alpha 1 plus 1, alpha 2 plus 1, and so on, alpha k plus 1. Number of even divisors of n. Now when I am considering the even divisors of n, at least one factor of 2 is required. So 2 to the power of 0 case we have to eliminate. So 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on. So for 2 to the power of alpha 1, the possibilities are alpha 1, Whereas for 3 power alpha 2, it is alpha 2 plus 1, alpha 3 plus 1, and so on, alpha k plus 1. Next, number of odd divisors of n. Number of odd divisors can be calculated from the total. You can subtract the even divisors, or we can calculate by eliminating the 2 to the power of alpha 1. That is, remove 2 to the power of alpha 1 and calculate the number of divisors for the remaining. So that will be alpha 2 plus 1, alpha 3 plus 1, and so on, alpha k plus 1. So the next is sum of divisors or factors of n is 1 plus p1 plus p1 square and so on, p1 to the power of alpha 1 into 1 plus p2 square and so on, p2 to the power of alpha 2 and so on, 1 plus pk square to the power plus and so on, pk to the power of alpha k. Now if I observe this 1 plus p1 square and so on, the geometric progression, and this can be written as p1 to the power of alpha 1 plus 1 minus 1 upon p1 minus 1, because number of terms is alpha 1 plus 1. In the same manner for the second and so on. Now this you can understood more clearly by taking an example. Let us consider the example 12, which can be written as product of primes as 2 square into 3 to the power of 1. Now if I consider without applying the previous knowledge, as writing directly the factors of 12 are 1, 2, 3, 4, 6 and 12. That means these factors I can obtain by using different possibilities of 2 power and different exponents of 3 power. That means I can use 2 power 0 or 2 power 1 or 2 square, and here 3 power 0 or 3 power 1. That means this I can rewrite as 1 plus 2 square into 1 plus 3. Now when I expand this product, the terms what I am going to get will be same as the factors of 12. That is 1 into 1, 1 into 3, and 2 into 1, 2 into 3, 6, and 2 square into 1 and 2 square into 3. That means the terms of this expansion will be same as the factors of the given number, and each factor is a geometric progression, so that you can write in this expansion of this form for the general one. So consider an example n equal to 10,800. So for this, find the total number of factors, number of even divisors, number of odd divisors, and number of divisors which are multiple of 15. So 10,800 you can write in as prime factorization 2 to the power of 4, 3 cube into 5 square. So total number of divisors or factors of 10,800 is 4 plus 1, 3 plus 1, 2 plus 1. So the product will be 60. Next, number of even divisors. So 2 to the power of 0 we need to eliminate. That means 4 into 3 plus 1 into 2 plus 1, which is 48. Number of odd divisors. Now that is from the total you can subtract the even divisors. So that is 12. Next, number of divisors which are multiple of 15. That means when I want to have a 15 as a multiple means 15 can be written as 3 into 5. So you take out 1 3 and 1 5 in this prime factorization. So when I take 1 3 and 1 5, remaining will be 2 to the power of 4, 3 square into 5. So for this, the factors of this can be obtained in the expansion of this. That is 1 plus 2 square plus 2 cube into 2 plus 2 power 4, 1 plus 3 square, 1 plus 5. So when I expand this, whatever the terms are going to get, the all are will be the factors of this, and we have kept 3 into 5 outside, means all will be the multiples of 15. And here number of terms are 5, 3 and 2. So 5 into 3 into 2, that is 30. That means number of divisors which are multiples of 15 are 30. So if there are n points out of which m are collinear, then how to find the number of lines that can be drawn passing through those points, and number of triangles that can be formed using those points. And another one is how to find number of diagonals of a polygon of n sides. So the number of lines that can be drawn is nc2 minus mc2 plus 1. Why nc2 is because you are having n points, and to draw a line we require 2 points. So the number of lines obtained is nc2, but in that m points are collinear. So all the m points form only one line. So I should subtract the number of lines which are obtained from m points, that is minus mc2. And when I am subtracting, the line itself also get eliminated. So I should add 1. Next, number of triangles that can be formed. To form a triangle, I should require 3 points. So I should select 3. That is NC3. But in this, again, there are some points which are collinear, which cannot be formed any of the triangles. So that's why we need to subtract minus MC3. Next, number of diagonals of a polygon of n sides. That means you will have n vertices. The definition of a diagonal is line segment joining non-consecutive vertices. Suppose if I consider all the line segments, then the number of line segments obtained means like each line segment can be joining by 2 points. So I can have, this is a one line segment, this is also one line segment. In this is one side and this is a diagonal. So the number of line segments means NC2. In that it is involving sides also. So to get the number of diagonals, I should subtract number of sides from NC2. That is NC2 minus n will give the number of diagonals, which is same as n into n minus 3 by 2. So the next point is number of rectangles of any dimensions or size in a square of dimension n by n, where n is a natural number. So here the rectangle contain what? Squares also of any dimension, means it can be 1 by 1 or 1 by 2 or 1 by 3 or 3 by 1 or 3 by 2 or whatever may be. Number of rectangles of any dimensions in a square of dimension n by n. Next, another one is how to find number of squares of any dimension in a square of n by n. Next, number of rectangles of any dimensions in a rectangle of dimension n by n, where m is greater than or equal to n. Next, number of squares of any dimension in a rectangle of dimension m by n, where m greater than or equal to n. So to find the number of rectangles of any dimensions in a square of dimension n by n, for calculation of this, let us consider an example of 4 by 4. Now, when I consider 4 by 4, horizontally I will have 5 lines and vertically also I will be having 5 lines. And to have a rectangle, I should choose 2 lines horizontally and 2 lines vertically, then a rectangle can be formed. That means choosing a 2 lines horizontally and vertically is 5c2 into 5c2. Now, when I generalize for n by n, it will be n plus 1 c2 into n plus 1 c2, which is same as n square n plus 1 whole square by 4, which is a formula for sigma n cube, which is same as sigma n whole square. Next, number of squares of any dimensions in a square of n by n. Now, again we can consider the same example of 4 by 4. Now, here I should count the 1 by 1 squares, 2 by 2, 3 by 3, 4 by 4. Now, 1 by 1 square, if I consider, there will be 16, which is same as what? 4 square. Now, 2 by 2, if I consider, 1, 2, 3. Again, 1, 2, 3. Again, 1, 2, 3. So, 3 into 3, 9. That means 3 square. Now, I can, in the same manner, I can consider 2 by 2, 3 by 3, and 4 by 4. So it will be 1 square plus 2 square plus 3 square and so on n square, which is same as sigma n square, which is the formula for n into n plus 1, 2n plus 1 upon 6. So basically we are identifying how many 1 by 1 squares are there, 2 by 2 squares are there, and 3 by 3 squares and 4 by 4 squares. So here we are considering 1 by 1, 2 by 2, 3 by 3 and so on n by n squares. Next, number of rectangles of any dimensions in a rectangle of dimension m by n, where m greater than or equal to n. Now, let us consider an example of 8 by 4. Now, when I consider 8 by 4, now here, because we need to calculate number of rectangles of any dimensions, that means I can have 1 by 1. Next, 1 by 2 and so on. That means 1 by 1 means 8 into 4. That means 32 rectangles will be there. Next, I can have 2 by 2. Next, So number of rectangles of any dimension in a rectangle of dimension m by n. Now, so instead of considering that, again here also I can say directly that if it is 8 by 4, horizontally 5 lines are there, vertically 9 lines are there. That means I should choose 2 horizontally and 2 vertically, which is same as 9c2 into 5c2. That is m plus 1 c2 into n plus 1 c2, which is similar to the previous 9th point. Next, 12. Number of squares of any dimension in a rectangle of dimension m by n, where m greater than or equal to n. Now, if I consider the same example, 8 by 4. Now, I should choose number of squares. That means the dimension should be, in this case, if I consider, it will be 1 by 1, 2 by 2, 3 by 3 and 4 by 4 only, because dimension here it is 4. Now here, when I consider m by n, the square dimension will be 1 by 1, 2 by 2, 3 by 3 and so on, n by n. So 1 by 1 in this example will be 8 into 4. Next 2 by 2 will be 7 into 3. 3 by 3 will be 6 into 2. 4 by 4 will be 5 into 1. Now when I generalize this, I can write as in sigma notation for this statement. Sigma m minus r plus 1 into n minus r plus 1, where r equal to 1 to n. And if I simplify this, then I can get the expression as n into n plus 1, 3m minus n plus 1 upon 6. And this formula will get coincide with when m equal to n, it will be the 10th one. That is n into n plus 1, 2n plus 1 upon 6.